We're going now to review some relevant information and some important information regarding signal-to-noise ratio and coverage. This is now the goal of this part of the session. The first thing to remember is that we are using on those phones very powerful tools for error protection and, if you want, detection and correction of errors. They are normally called forward error correction codes, or FEC, in the sense that you send the data and all the detection and correction has to be done on the receiving end. In general, you require this when it's not easy or you cannot resend the data. And those phones do this also adding redundancy check, adding bits, and also interleaving. Interleaving just means that mixing the bits in a way that is convenient. For instance, a simple example of interleaving would be the following. Assume you have a set of bits, having a stream of bits, and you start to store them in a matrix, and the first bits go to the first row, the second set to the second, the third, and you just have the bits arranged in a matrix along the files. But when you read the bits, you don't read them following the files, you read them in the columns. You can still identify the procedure where those bits come from, but then you mix them. In this way, if there is a loss of just a few consecutive bits, you are not losing the whole information, you just disperse the loss along different words or different sets of bits. This is called interleaving, and those systems interleave the bits with this time range, 10, 20, 40, or 80 milliseconds, which is just a very powerful, very strong interleaving. They employ normally a couple of codings for the channel coding process, and it's a half rate and 1/3 convolutional codes, which are constraint length 9 codes. This for low data rate connections, and for high data rates they use turbo coding. So they have different coding schemes for protecting against error. Another powerful tool is power control. And on those phones you have to implement power control. Why? Because assume you are very close to the base station and there is another user that is far away. Then you will be blinding the faraway phone if you are transmitting too much power. So what the base station does is to control the power of your phone and bring it down to a level that could avoid this effect. This effect is known as near-far effect, and it's present in all those phones. And there are two ways to control the power. The first, before calling the power, the base station, the receiver on the base station could estimate your propagation loss and will tell your phone to use a certain power. But once you start to transmit, then it measures the signal-to-noise ratio and adjusts it to the target value. And it does this on those phones once per time slot. That means 1500 times per second. So your phone is being controlled at a very fast sequence, and the power is really changing depending on your environment, other users, how close you are to the base station, buildings, whatever is around you. And this power control is a quite a strong tool to mitigate fading in mobiles that are not moving very, very fast. So this is an important factor. This is on the good side. On the bad side is that all spread spectrum signals look like noise. So if you are not the only user, and certainly you are never the only user on a cell, that means that all other users are going to interfere with you. And this level of interference is going to be dependent on the traffic load in this cell. So this traffic will contribute directly to a raise in the noise level. And you have to consider them. And this is the way it's normally done. The interference level is just dependent on the load factor, and The higher this load, certainly the larger the interference. The lower this value, the lower this will be. So in this case, this is just the main parameter. So the interference level is depending on the load factor. And the load depends on the number of active users or active sessions in this cell. So for the uplink, assume you have n users in the cell, then you can write the load factor as dependent on two things: the number of users in your cell and also the interference that your neighboring cells will just also be in some way affecting you. So those two terms, the intracell and the intercell, are modeled in this way. And the parameters that are involved in this formula are defined in this one. And here you have some typical values. The load factor, the typical load factor for the uplink is somewhere around 0.5 to 0.8. The interference from other cells to yours is typically around 0.6. N is the number, this is the chip rate. And this interference depends also on the energy of the other users and another important parameter, the bit rate, and the activity factor of a user. And this is something that you should take into account. Those phones are very efficient. If you are not talking, at the instance of times where you are silent, they don't send anything. So for a typical voice activity, you normally never use more than 67%. And if you consider that half of the time you are talking and half of the time you are listening to your correspondent. But for data, this could be totally different depending on what you are doing. If you are just browsing on the web, maybe you send some data, you wait, so there are moments where you will have almost no activity. But if you are, in some way, you are transferring, you are downloading a heavy file, then probably the data is going to be coming to you at a very, very continuous rate. So the activity is going to be highly variable in those systems, in those phones. Now, those parameters influence the signal-to-noise ratio, but also the place you are talking is going to have also an important effect. It's not the same if you are just talking from the car, you are driving on the highway and you are just receiving a call, or you are sending data in the middle of the university of the campus, or you are inside the building, you are in an office or at home, and you just want to have a data connection. So in those cases, things are totally different. This is a very complex and complicated environment, and there are some models. There are different models. Each one will give you very different values, but today we are going to just consider one of them, and it's based on the Okumura-Hata model that was extended to the UMTS or 3G bands by the CORS 231 project. And this model for an urban macro cell, that means in a medium-sized city, it gives you the median path loss, L, as a function of the mobile antenna height. We take the standard 1.5 meters. This is the normal thing to do. In terms of the frequency in megahertz, in this band, if you are using different frequency bands, go for another models, find the parameters, because all those models are different. They all try to fit experimental data into some numerical model. HM is the antenna, the phone antenna. HB is the base antenna in meters, appears here and here. And D is the range, is the distance from the base station in kilometers. It should be less than 20 kilometers for this model, but normally it's much less than that. And with these numbers, you get the median path loss for this environment. If you are not in the middle of the city, but you are in other environments, then you have to add correction terms, and here you have some that are used for this band. If you are in a large city, in a metropolitan area, you add 3 dBs. If you are in the suburban area, things are better, so you have to subtract to the urban, to the city, some values here. If you are in a rural environment, you will still take out some other things. If you are in a highway, and this is just a nice open area, but then you have a different model. These two are the same, they only differ in 5 dBs. So this is just one of the models, but you can have some others, and they should fit in your data. But that's not enough. Besides this, we have to add margins. We have to take care that things could not be as good as expected. And since those models, they just compute median values, then we have to see how the real environment could change those values. And we have 2 important effects. One is described as slow fading. That means that the signal you receive changes slowly with respect to the median, to the mean value, and it's normally due to shadowing by buildings, the terrain, the trees, whatever, depending on where you are. And normally this fading is modeled by a log normal distribution. And for this log normal distribution, you can take different parameters, but an important one is the coverage, the probability of coverage. That means in a cell, what is the percentage of sites you want to cover? You know that in a cell, if you are close to the base station, this is really good, but if you are near the edge, things could be really bad. So depending on the percentage of sites you want to cover, this is a parameter that will enter this distribution. And then also you have to consider the standard deviation depending if you are indoors or outdoors. In the examples, we are going to include a fading margin of 7 dBs in our calculations. But there's another fading which is very fast. It happens really with very short delays and also with very deep fadings. Could go up to 20 dBs or more. And this is due to multipath propagation and phase cancellation. For instance, just to see something which is clear, at 2 GHz, half a wavelength is 7.5 centimeters. That means that if you have 2 paths that only differ in 7.5 centimeters and the amplitudes are equal, then when you add them, they will cancel. This fast fading is normally modeled by a Rayleigh distribution. Sometimes Rice, but Rayleigh distribution is the most frequently used. But fortunately, in 3G phones, this is much easier to handle than in the 2G phones. Why? Because the chip length here, the code length, which is 3.84 megahertz per second, that corresponds to 78 meters at the speed of light, helps a lot and allow the receiver to deal with this fade, and at the end you may be needing only a margin of 2 to 5 instead of the values that were normal in 2G phones. In the examples you are going to see afterwards, we are going to include a fast fading margin of 4 dBs. But since we are going to consider the case of a car in a highway, in this case we will not be using any margin, no margin will be required. And since one mobile phone could be connected to more than one base stations, when this happens, then we have a gain. This is in our favor. The previous 2 fadings were against us as users. Now this one will help you. And typical values for this gain, when it's present, is between 2 and 4 dBs. We will include, in our case, a 4 dB gain for this case. And this is just the basic parameters for the margins that we should consider in signal-to-noise ratio and coverage studies.